Here is something worth thinking about as you settle in tonight. Right now, at this very second, tons of material are hanging above your head. The ceiling, the floor above, the walls, the roof, all of it is pushing down, and pushing hard. The building you are in weighs hundreds, maybe thousands of tons. And all of that mass is making a journey right now. A slow, invisible, continuous journey downward, toward the ground. Gravity is pulling on every brick, every beam, every bolt. And that force has to go somewhere. It has to find a path through the structure, through the foundation, through the soil, and into the earth. And if anything along that path goes wrong, if any single element cannot handle the load, if any connection turns out to be too weak, the structure collapses. But it does not collapse. It stands, quietly, reliably, invisibly, and you do not even think about it. Now picture a different kind of structure. Imagine 4 concrete legs, each as tall as the Eiffel Tower, reaching 1,000 feet down into the dark, freezing water of the North Sea. At the bottom, 19 hollow concrete chambers pressed into the seabed like upside-down coffee cups. 5 million waves crash into each of those legs every single year. The water pressure outside is 30 times greater than the air pressure inside. And up top, 250 feet above the waterline, an entire chemical plant, a drilling rig, living quarters for hundreds of people. And all of it stands, has been standing for decades, in one of the most hostile places on the planet. How? How is that possible? How did people learn to build structures that do not fall down? In cities, in mountains, in the middle of the ocean. And here is another thing. A Roman aqueduct in the south of France has been standing for 2,000 years. A Gothic cathedral in Cologne took 600 years to build and still is not finished. A dome in Florence weighs 25,000 tons, and it holds itself up with no support from below. And twin towers in Madrid lean 3 times more than the Leaning Tower of Pisa, on purpose. What do all of these structures have in common? The same task, the same struggle. Take the force that pulls everything toward the ground and guide it through a structure in a way that nothing breaks. Today, we are going to walk that path together, slowly, without rushing, from the very beginning. We will start with stone and the arch, with how the Romans, 2,000 years ago, found the simplest and most beautiful way to span an open space. Then we will climb higher, to the Gothic cathedrals, where medieval stonemasons built buildings that still stand today without a single formula. We will crawl inside Brunelleschi's dome in Florence and understand what makes a dome fundamentally different from an arch. We will trace how the arrival of iron and steel changed everything, and how one French engineer named Gustave Eiffel went from building railway bridges to the most famous tower in the world. We will descend into volcanic soil near Naples, where the Romans accidentally invented concrete, and see how that material reached the avant-garde bridges and railway stations of the 20th century. We will stand at the base of the Leaning Tower of Pisa and understand why it leans, then travel to Madrid, where leaning buildings were built deliberately, with 14,000 tons of concrete in the foundation as a counterweight. And finally, we will head out to sea, to lighthouses, storm barriers, and oil platforms, where engineering fights its most relentless opponent of all. And along the way, if we are lucky, we will understand something about the nature of engineering thinking itself, about how people have been making decisions under total uncertainty for centuries, about how every disaster gave birth to a new rule, and about why the best engineering is the kind you never notice. We will take apart each of these structures slowly, with stops along the way. We will pause and explain things that seem obvious, because often the most obvious things turn out to be the most interesting when you look closely. Why is stone strong in compression but weak in tension? Why is the triangle the strongest geometric shape? Why can a dome have a hole at the top and still not fall? Why is a curved surface stronger than a flat one? Each of these questions sounds simple, but the answer opens up an entire world. Take your time. Get comfortable. If you drift off somewhere along the way, that is perfectly fine. The story will be here. Have you ever thought about what happens when you walk upstairs? Your weight, say 150 pounds, presses down on the floor. The floor is a horizontal slab, and it bends. Just the tiniest bit, invisible to the eye, but it bends. That bending creates forces inside the slab. The top surface compresses, the bottom surface stretches. The slab passes your weight to the beams. The beams pass it to the walls or columns. The walls and columns carry it down to the foundation. The foundation spreads it across the soil. And somewhere down there, in the body of the earth, your 150 pounds dissolve, distributed across an area, and the ground accepts them without the slightest effort. All of this happens instantly, continuously, silently. You walk, you sit down, you jump, you put a bookshelf against the wall, you fill the bathtub with water, and with every action, the forces redistribute, find new paths downward, adapt. The structure lives. It breathes with loads the way your lungs breathe air. And the most amazing part, you feel none of it. The structure is designed so that you never, not for a single second, wonder whether it might give way. That is the highest compliment you can pay an engineer, when nobody notices their work. Let us start with stone, the simplest stone there is, and with a question that seems obvious until you actually try to answer it. How do you span an empty space? In the south of France, not far from the city of Nîmes, stands a structure that made the philosopher Jean-Jacques Rousseau say he felt like an insect lost in the immensity of the work. The Pont du Gard, a Roman aqueduct, built most likely in the 1st century AD. It carries water across the valley of the river Gardon, a tributary of the Rhône, at a height of 157 feet. 3 tiers of arches, 6 on the bottom, 11 in the middle, 35 on top. The tallest bridge the Romans ever built, and it is still standing, 2,000 years later. To understand why it stands, you first need to understand what stone does. Stone is a peculiar material. It is incredibly strong when you squeeze it. You can place an enormous load on a block of stone, and the block will not budge. But try to pull stone apart, and it cracks almost immediately. Stone handles compression and hates tension. This is a fundamental property, and it determines everything you can build out of stone. Now imagine you need to span a gap, a river, say. The simplest way is to lay a stone slab across 2 banks, a log over a stream. But what happens to that slab when something pushes down on it? The weight of a person, for example. The top surface of the slab compresses, and stone handles that just fine. But the bottom surface, it stretches. The slab bends, and tension appears underneath. And stone cannot take that. So a stone beam cannot be very long and cannot carry much weight. For a small stream, sure. For a wide river, no longer possible. The Romans knew about this limitation, and they found a solution that changed the history of building forever. The arch. Look at any arch on the Pont du Gard. It is made up of stones, each one slightly wedge-shaped. The stones are laid in a semicircle, and each one presses against its neighbour. When weight pushes down from above, the weight of the water in the aqueduct, the weight of the stones themselves, the weight of everything above the arch. That weight does not bend the arch the way it would bend a slab. Instead, each stone passes the pressure to its neighbour. The force flows along the curve of the arch from stone to stone, from the top, down and outward, until it reaches the supports, the piers, the pillars on which the arch rests, and from there, down into the ground. Think about what is happening here. Every stone in the arch is working only in compression. Not a single one is being stretched. The entire structure uses the one strong property of stone and completely avoids its weak one. The shape of the arch is a way to make gravity do what the builder needs. Instead of pulling the structure down and breaking it, gravity presses the stones together and makes the arch stronger. There is a simple way to feel this yourself. Put your hands together in a tent shape, the fingertips of your right hand pressing against the fingertips of your left. Now, have someone push down on top of your tent. What do you feel? Your fingers compress. The pressure travels down your arms to your wrists. Nothing stretches. The downward pressure turns into compression along your fingers. That is the principle of the arch, in miniature, on your own body. Now imagine removing one finger from the tent. The whole thing collapses. An arch works the same way. Every stone is essential. Remove one, and the curve breaks open. But as long as every stone is in place, each one supports its neighbour, and the system is incredibly strong. A completed arch can carry a load many times greater than its own weight. Additional weight on top does not weaken the arch. Paradoxically, it makes it stronger, pressing the stones together even more tightly. That is why Roman aqueducts survive earthquakes, floods, and centuries of weathering. As long as the arch stones are in place and the piers are standing, the arch will stand. It will only fail when the stone physically crumbles from age. And good stone, granite for instance, can last for thousands of years. That is why the arch is one of the most brilliant inventions in the history of building. It takes a weak material, stone, which cracks under tension, and creates a structure in which tension simply does not exist. But the arch has one feature you need to keep in mind. The force travelling along the curve of the arch does not just push straight down onto the supports. It also pushes outward to the sides, trying to spread the supports apart. If the supports are not heavy enough or strong enough, the arch simply slides open and the stones come tumbling down. So every arch needs massive supports, or something to resist that lateral thrust. Remember this, because the fight against lateral thrust is one of the central themes in the entire history of building. It will haunt engineers from Roman aqueducts all the way to modern domes. Now let us go back to the Pont du Gard and look at the details. The stones making up the arches are over 3 feet thick. That is roughly 1/20th of the arch's span. The Romans never made sophisticated calculations. They had no formulas, no theory of elasticity, no concept of stress and strain. They knew from experience that if the stones of the arch were thinner than a certain proportion, the arch would collapse. And that proportion, roughly 1/20th of the span, was an empirical rule that worked. The builder on the construction site did not calculate the resistance of materials. He followed a rule passed down from master to apprentice, from generation to generation. And you know what? That rule has been working for 2,000 years. The Pont du Gard is still standing. Between the arches and above them are the spandrels, solid stone infill. Spandrels look like part of the structure, but they actually serve a very simple function. They transfer the load from above onto the arch, distributing it more or less evenly. They do not need to be made of strong stone. Behind the stone facing of the Pont du Gard's spandrels is just compacted rubble fill. All the builders needed was for the mass above to press down on the arch fairly evenly, and the arch did the rest. At the very top, along the uppermost tier, runs the water channel. It is quite small, about 4 feet wide and a little over 3 feet deep. And it is the only part of the entire aqueduct where mortar was used, for waterproofing. Everything else is dry-laid masonry, stone on stone, with no binding agent. Only weight and shape hold the structure together. How did the Romans build these arches? The process was both simple and risky. First, the supporting piers were erected, massive stone pillars. Then wooden centering was placed on top, temporary semicircular frameworks of timber that held the stones of the arch until the arch was complete. Stones were laid on the centering from both sides simultaneously, gradually rising toward the top. The last stone to be placed, at the very peak of the arch, was called the keystone, and that was the most critical moment. When the keystone dropped into place, the arch locked and became self-supporting. The wooden centering was removed, and the arch stood. Or it did not. But if all the proportions were right, if the stones were thick enough and the piers massive enough, the arch stood. And it stood, essentially, forever. One important limitation that determined the size of Roman arches was purely practical. The stones had to be lifted into place. The Romans used wooden cranes, powered by teams of slaves. The biggest crane they had could reach about 50 feet. If you placed 2 cranes on either side, the maximum arch span came out to less than 100 feet. And indeed, the longest spans on the Pont du Gard are about 80 feet, close to the limit. So the size of the arch was determined not by the strength of the stone or by engineering calculations, but by the reach of the crane. Construction technology limited form. And when the span needed to be wider, the Romans simply built more arches. Valley too wide for a single span. Put 6 arches in a row. Aqueduct too tall. Stack arches 3 tiers high. The solution was simple, practical, and it worked. When you look at the Pont du Gard from the side, you might notice the whole bridge leans slightly in one direction, tilting toward the upstream side. This happened over 2,000 years. Water undermined the piers on one side a little more than the other, and the bridge shifted. But it did not collapse. Masonry is incredibly tolerant of deformation. It can shift, it can twist slightly. Individual stones can crack, and the structure still stands. You would have to try very hard to bring down a well-built stone arch. When you stand on the Pont du Gard and a load passes over it, you can feel vibration. The whole structure trembles slightly. Eiffel, whom we will talk about later, calculated that his arch would deflect just 1/3 of an inch under the weight of a train. Roman engineers did not make such calculations, but they knew from experience that a structure needs to breathe, to bend slightly under load and spring back. A perfectly rigid structure is dangerous. It gives no warning of overload. A flexible one bends, and the bending is visible. The Romans, of course, did not put it that way. They simply built and noticed what worked and what did not. In 1747, 17 centuries after the original was built, a pedestrian bridge was added next to the aqueduct, its stone arches exactly echoing the Roman originals. The most dangerous moment in building any bridge is just before completion. When the structure is nearly done, but not yet locked together, it is at its most vulnerable. Roman builders must have felt that every time they set a keystone. The moment the centering is removed, and the arch either stands or falls. No trial run, no way to test in advance. Either everything is calculated correctly, or catastrophe. The main contribution the Romans made to the history of building was process, organization, scale. They did not invent the arch. Arches existed before them. But they were the first to use the arch systematically, on a massive scale, as a universal building element. Aqueducts, bridges, amphitheaters, vaults, arches everywhere. They perfected it not through theory, but through practice. Tens of thousands of arches built across the empire, each one teaching builders a little more about what works and what breaks. And here is the thing. The arch of the Pont du Gard is semicircular, a perfect half circle. The Romans almost always build semicircular arches because a semicircle is easy to lay out with a rope and a stake. Plant the stake, stretch the rope, trace the curve. There is your centering template. The semicircle is the simplest shape to lay out and the most reliable to build. Roman engineers trusted this shape because it had proved its strength for centuries. But the semicircular arch has one property that limits its use. The height of a semicircular arch always equals half its span. If the span is 30 feet, the arch rises 15 feet. If the span is 60 feet, 30. You cannot make a semicircular arch taller or shorter without changing the span. Height and width are locked together. And that means if you need to span a certain width but want the ceiling to be higher, the semicircular arch will not work. You need an arch of a different shape. And so, 1,000 years after the Pont du Gard, people appeared in Europe who wanted to build higher than ever before. They wanted their buildings to literally reach the sky. And to do that, they had to change the shape of the arch. The 12th and 13th centuries in Europe were a time of extraordinary building frenzy. Trading cities had grown rich, religious fervour was at its peak, and across the continent a genuine race was underway. Who could build a cathedral taller, more magnificent, more full of light than the neighbours? This was the age of High Gothic. And if you have ever walked into a Gothic cathedral, you know the feeling. You tilt your head back and the space above you simply does not end. Slender columns shoot upward, and somewhere impossibly high merge into stone vaults. Light pours through enormous stained glass windows. Everything seems weightless, floating, almost impossible for a stone structure. Cologne Cathedral in Germany is one of the most striking examples. Work began in 1248, and the cathedral was built, rebuilt, and extended over 600 years. The towers on the west facade were not finished until the 19th century. There is a local saying, "When the cathedral is finished, the world will end," because restoration work never stops. The exterior of Cologne Cathedral is lavishly decorative, almost excessive. But all that decoration conceals a remarkably simple structure of arches and vaults that owes a great deal to the very same Romans we just talked about. At its core, the structure of Cologne Cathedral is built entirely on arches, just like the Pont du Gard. Stone elements work in compression, and gravity travels downward along curves and columns, passing into the foundation and on into the ground. But here is the key difference. The semicircular Roman arch has been replaced by the pointed arch. And this change, for all its seeming simplicity, made an entirely different kind of building possible. Let us work out why. Remember that the semicircular arch has a fixed ratio of height to width. Height always equals half the span. The pointed arch, two curves meeting at a peak, lets you change that ratio. You can make the arch narrow and tall. You can make it wide and shallow. Height and span are no longer locked together. That gives the architect a freedom that Roman builders simply did not have. But freedom of shape is only part of the advantage. Far more important is that the pointed arch directs forces more vertically. In a semicircular arch, a significant part of the force goes sideways, that same lateral thrust we talked about. The supports have to be massive to handle that pressure. In a pointed arch, the force travels more steeply downward, more directly. The lateral thrust is smaller. And that means the supports can be thinner. Think about what that gives you. Thinner supports mean thinner walls. And thinner walls mean room for windows. Big windows. Enormous stained glass windows that flood the interior with light. The pointed arch is what made those breathtaking stained glass panels possible in Gothic cathedrals. The semicircular arch required thick walls for support. The pointed arch freed the walls, and they became screens for light. And one more thing. Because the pointed arch carries force downward more efficiently, it can be thinner than a semicircular arch of the same span. Less stone, less weight. You can build higher. The symmetry of the pointed vaults and the clean vertical lines of the columns are what give Cologne Cathedral its distinctive elegance. That feeling of lightness and height, so different from the squat power of Roman buildings. But building high creates new problems. The weight of the roof pushes down on the tall vertical columns and shoves them outward. The taller the column, the harder it tries to topple. The columns need to be braced from the outside. But the cathedral is much narrower at the top than at ground level. Down below, the side aisles and galleries take up a lot of space. The bracing for the upper level has to leap over the lower level, reach the outer walls, and from there, send the force down into the ground. The solution the Gothic builders found is one of the most beautiful in the history of architecture. flying buttresses. All around the perimeter of the cathedral, the upper levels are supported by these graceful half arches, thrown across empty space from the nave walls to the outer buttresses. They are essentially flat arches, and they work exactly like the arches of the Pont du Gard. Force is carried along the curve from the point where the vault pushes against the column, down and outward to the massive buttress, and the weight of the buttress directs that force down to the ground, preventing the flying buttress from toppling over. At the top of each buttress sits a pinnacle, a decorative turret. It looks like an ornament, but it actually serves a structural purpose. It adds weight to the top of the buttress. Without that extra weight, the arch of the flying buttress could break the upper part of the buttress away from its base. The pinnacle prevents this by loading the buttress from above. Beauty and function coincide here, which in Gothic architecture happens more often than you might think. Now consider this. All of these structural solutions, the pointed arch, the flying buttresses, the pinnacles, were developed by people who had not a single formula for calculating loads. The master masons who built Cologne Cathedral did not know the words compression and tension in a scientific sense. They had no theory of elasticity, no concept of torque, no way to calculate the exact force acting at any specific point in the structure. They worked from geometric rules of proportion, handed down from generation to generation in Masonic lodges, closed professional guilds of stonemasons. These rules were originally developed by the ancient Greeks and refined over centuries of practice. A mason knew, if you build a structure strictly according to these geometric rules, it will stand. Why it would stand, the mason could not explain. The scientific understanding of what forces are at work in a Gothic cathedral and why those proportions hold came much later. But the rules worked, and buildings constructed by those rules have been standing for nearly 1,000 years. Vaughn Koen, the author of The Engineering Method, calls this approach heuristic. A heuristic is a rule that does not guarantee a perfectly precise result, but will very likely lead to a good solution. Arch stones should be 1/20th of the span. That is a heuristic. Wall slope should be 1:5. That is a heuristic. An engineer, according to Koen, always works with incomplete information and always uses the best available solution. Not the perfect one, but the best one currently at hand. Medieval masons did exactly this. They had no way to calculate everything precisely, but they had centuries of experience compressed into a set of geometric rules. And that was enough. The pointed arch was not the only invention of the Gothic builders. They also developed the ribbed vault, a system of stone ribs forming the skeleton of a vaulted ceiling. The ribs carry the main load, and the space between them can be filled with thinner, lighter masonry. In essence, the Gothic builders invented the frame structure, a principle that 5 centuries later would become the basis of steel and reinforced concrete construction. The frame carries the load. The infill does not. This saves material and reduces weight, which means you can build higher. The ribbed vault also allowed builders to span rooms of irregular shape, rectangular, trapezoidal, triangular. The semicircular arch required all spans to be the same width, or else arches of different widths would reach different heights and fail to meet at the top. The pointed arch does not have that problem. You can vary the sharpness of the point, adjusting the arch's height to fit the span, and all the ribs will meet at the keystone at the same height, regardless of span width. That is an enormous freedom for floor plans. Cologne Cathedral has its roots in the great French cathedrals, Notre Dame, Reims, Amiens. The master mason Gerhardt, who laid down the plan, travelled to France, studied the construction of French cathedrals, and brought back the knowledge and techniques. After his death in 1260, many other masters continued the work, but it was his vision that shaped the cathedral we see today. Stone was shipped down the Rhine from the Drachenfels, 25 miles upriver. The master mason oversaw the entire construction, combining the roles that today belong to architect and engineer, and organizing the teams of professional craftsmen. These were highly valued, sought-after specialists. The cathedral survived difficult times. During the Second World War, bombs brought down 10 vaults in the nave and north transept. One bomb damaged a tower so badly that the damaged section had to be filled in with brick. It was left that way deliberately, as a reminder of those years. In 1992, an earthquake knocked the top off one of the pinnacles. A major restoration program is now underway. Decades of air pollution have turned the white stone almost black, giving the cathedral a grim, almost threatening appearance. Henry Petroski, in his book To Engineer is Human, writes that medieval cathedral builders were, in essence, the first systems engineers. They managed enormous projects that lasted decades, sometimes centuries. They coordinated the work of hundreds of people. They solved logistics problems, transporting stone by river, setting up lifting mechanisms, supplying the site. And they made structural decisions on which the lives of workers and worshippers depended. When a vault collapsed, and it did happen, the masons analyzed the cause and made adjustments. Every failure became a lesson. The cathedral at Beauvais, for instance, attempted to break the record for vault height, and part of its vaults collapsed in 1284. After that, builders understood that there was a limit, a height beyond which stone vaults could not hold. That lesson was absorbed by every subsequent generation of builders. Knowledge spread through the Masonic lodges, through itinerant masters who moved from one site to another, carrying experience and warnings. Koen would call this the state of the art, the best available knowledge at the time. Every cathedral, every collapse, every successful structure updated that state of the art. The next cathedral was slightly better than the last, not because the masters had gotten smarter, but because they had more of other people's experience to lean on. Let us look at the path of force through a Gothic cathedral, the thread running through our entire story. In a Gothic cathedral, gravity takes a winding, ingenious path from roof to ground. It starts on the stone vault, which pushes down and to the sides. The pointed shape of the vault directs most of the force downward, but the remainder goes sideways. That remainder is caught by the flying buttress, which throws it across the void of the side aisle to the outer buttress. The buttress, weighted down by the pinnacle, directs the force vertically down into the foundation, and the foundation passes it into the ground. Every element, vault, column, flying buttress, pinnacle, is one link in a chain along which force travels from sky to earth. Remove any link, the chain breaks and the structure falls. That is why, when wartime bombs brought down 10 vaults in Cologne Cathedral, the damage did not spread to the whole building. Each vault is a relatively independent structural unit, and the collapse of one does not drag down its neighbour. The Gothic builders, without knowing it in the terms of modern engineering, had intuitively designed a system with a degree of redundancy. Each element could lose its neighbor without failing itself. With just simple hand tools, wheelbarrows, and winches, the builders of these Gothic cathedrals completed the most complex industrial projects in Europe since Roman times. Their organization of the construction site into teams of paid professionals rather than slaves was fundamental to their success. But what strikes me most is what they achieved technically in a pre-scientific age. Without a single formula, without a single instrument for measuring loads, only geometry, experience, and professional intuition. The pointed arch and the flying buttress gave builders the ability to create tall, light, awe-inspiring spaces. Stained glass windows and high stone vaults grew ever wider and more magnificent as cities and nations competed with one another. But arches and vaults, for all their beauty and efficiency, span space in one direction. A vault bridges a gap from wall to wall. But what if you need to span not a gap, but an area? What if you need to cover a huge space, round, octagonal, square, without a single column inside? For that, you need an entirely different kind of structure. A structure in which forces spread not along a single line, but across an entire surface. A structure that can have a hole at the very top and still not fall. A structure that one Italian republic spent 60 years building with no idea how to finish it. No other city in Europe, except perhaps Venice, lives off its past quite the way Florence does. The list of geniuses who lived and worked here reads like an encyclopedia of art and literature. Dante, Michelangelo, Brunelleschi, Giotto. And that is just the beginning. But for any visitor picking their way through the Florentine streets, there is one building that follows you around every corner, flashes above the rooftops, rises behind every turn. It has dominated the city skyline for over 500 years, Brunelleschi's dome. The Cathedral of Santa Maria del Fiore. And the story of this dome is one of the most astonishing in all of building history, because the cathedral was essentially finished 60 years before anyone figured out how to put a roof on it. Let us start at the beginning. Construction of the cathedral began in 1296. The project was ambitious. Florence wanted to build something that would eclipse every rival. A cathedral with an octagonal base for a dome that would span 148 feet. For comparison, the largest Gothic vaults of that era were 2 or 3 times narrower. 148 feet, that was beyond anything built in medieval Europe. The cathedral took half a century to build. Walls went up, naves were vaulted, the octagonal drum, the base for the future dome, rose higher and higher. By 1357, the cathedral was essentially complete. The walls stood, the drum was ready. All that remained was to cover that enormous octagonal opening with a dome. And then, everyone stopped. Because nobody knew how to do it. The traditional method of building domes at the time relied on wooden centering, temporary support structures on which stones or bricks were laid until the dome locked together and became self-supporting. The same principle as building arches. Remember the centering at the Pont du Gard? But here the span was so enormous that no wooden structure could bridge it. There simply were not long enough timbers or strong enough joints to build centering at 148 feet. It would have collapsed under its own weight. The result was a paradox. The Florentines had started a project without knowing how to finish it. They built a cathedral with a hole in the roof, and that hole stayed open for 60 years, from 1357 to 1418, when a competition was finally announced for the dome's design. The competition was won by Filippo Brunelleschi, a goldsmith and sculptor by training, with no formal architectural or engineering education. He proposed an idea that seemed insane to everyone. He declared that he would build the dome without any centering at all. No support from below whatsoever. The dome would be self-supporting at every stage of construction. How? Brunelleschi argued that if the dome were built in rings, horizontal courses of bricks, each one closed into a ring, then each ring would support itself. No need to wait for the entire dome to lock together. Each completed course of masonry was already stable. You could simply lay course after course, climbing higher and higher, and at every level the structure would be sound. This principle had been used before, but never at this scale. Convincing the clients was not easy. Brunelleschi built a model about 12 feet across and conducted a series of impressive demonstrations before he won the contract. Construction took another 16 years. Let us climb inside and see how this dome works. One of Brunelleschi's major innovations was a double shell. The dome consists of an inner and an outer layer, separated by a space you can walk through. Staircases run between the shells, allowing you to climb from the base to the very top. The inner shell is thick, over 6 feet at the base. The outer one is thinner, protecting the structure from weather and giving the dome its distinctive silhouette. The total thickness of the structure is over 13 feet, and the entire dome weighs 25,000 tons. That is a colossal weight, and it creates a colossal problem. Because a dome, like an arch, does not just push downward, it pushes outward. A dome carries its weight down and to the sides, and around the perimeter it needs support to keep it from cracking vertically. Remember the arch, it has the same problem. But a dome is essentially an arch rotated around its axis. Lateral thrust acts in every direction at once. Historically, large domes were reinforced from outside, with massive buttresses resisting the thrust. In Florence, 3 small domed apses provide some support. But Brunelleschi understood that this was not enough for such an enormous dome. So he used a system of stone chains with iron links, encircling the dome around its perimeter. These chains work like hoops on a barrel. They pull the dome inward and prevent it from spreading. But even all these systems were not enough to completely prevent movement. If you look at the inner surface of the dome, you will see vertical cracks running along some of the faces. Many people think that cracks mean the building is about to collapse. They do not. Masonry can handle quite significant movement before it actually fails. The cracks look alarming, but the structure is far from its breaking point. The dome has been standing for 500 years and will stand for another 500, cracks and all. Now, an important point that separates the dome from the arch. An arch has a keystone, that final stone at the very top that locks the structure together. Without the keystone, the 2 halves of the arch would fall toward each other. A dome can have a hole at the top and still not fall. Why? Because in a dome, forces spread across the entire surface of the shell, in all directions. Every stone pushes against its neighbor to the right and left, above and below. Forces radiate across the whole surface like ripples on water. And at the very top, you can leave an opening, a lantern, through which light enters the cathedral. Because the ring of stones around that opening carries the load by itself, distributing it around the full circumference. That is the fundamental difference between a dome and an arch. An arch carries force along a single line, along its curve, from the top down to the supports. A dome carries force across its entire surface, in all directions at once. That is why a dome can span much larger gaps than an arch, and be thinner while doing it. And think about it. 25,000 tons of brick, stone and mortar lifted to height without a single crane in the modern sense. Only winches, pulleys and muscle power. Brunelleschi invented several lifting mechanisms specifically for this project, including a system that allowed an ox walking in circles on the ground to raise heavy loads to the top of the dome. Inside the dome, between the shells, is an entire hidden world. Staircases spiral upward, passing through massive ribs that tie the inner and outer shells together. Brick courses in a distinctive herringbone pattern, the same technique the Romans used, stretch up toward the vanishing point. Through windows you can peer down into the cathedral interior, where Vasari's frescoes use the octagonal shape of the dome as a frame. Hell portrayed at the bottom, heaven above, crowned by that fantastic false lantern at the very top. Brunelleschi's dome in Florence is a structure standing at the crossroads of two eras. It caps the medieval tradition of building with stone and brick, pushing it to the absolute limit of what was possible. And at the same time, it opens the Renaissance, an age when engineering began to rely not only on experience and tradition, but also on observation, experiment, and individual genius. Looking at this dome today, its 148-foot span might seem modest by current standards. But for the better part of 400 years, the Cathedral of Santa Maria del Fiore had the largest dome in the world. An amazing and unique achievement. The dome still dominates the city skyline in a way unmatched anywhere else, and is recognized worldwide as the greatest masonry dome in existence. The method Brunelleschi developed set a standard that was followed for centuries, right through the building of the great domes of St. Peter's in Rome and St. Paul's in London. Domes remained stone, massive, heavy, because stone and brick were the only materials available for such structures. But in the 20th century, new materials appeared, and these materials allowed domes to become something entirely different: thinner, lighter, larger. So much thinner that if you placed Brunelleschi's dome next to a modern dome of the same diameter, the difference would seem impossible. 13 feet of thickness versus 2.5 inches. 25,000 tons versus a weight less than a single floor of an ordinary office building. How did that become possible? The answer lies in a material that the Romans accidentally invented 2,000 years ago, and that waited for its moment until people learned how to reinforce it. Not far from Naples, in the shadow of Mount Vesuvius, is a place where the Romans accidentally made one of the most important discoveries in the history of building. The town was called Puteoli. Today it is Pozzuoli. And the discovery was this: if you used volcanic ash instead of ordinary river or beach sand, that same dark, porous rock that Vesuvius spews out, the concrete you got was incredibly strong. So strong that it would even set underwater. The Romans did not understand the chemistry of the process. They simply noticed that builders in the Pozzuoli area produced concrete of far better quality than anywhere else. The volcanic sand changed the chemical reaction in the cement, creating a crystalline structure that was much stronger and more durable than anything made with ordinary sand. This new cement was named Pozzolana, after the town where it was first discovered. And by the middle of the 1st century BC, Pozzolana had become a key component of every major Roman building project. Let us work out what concrete actually is and why it works. Concrete is a mixture of stones, sand, and cement. Cement is the binding agent that glues everything else together. When you add water to dry cement, a chemical reaction begins. Crystals form that stick to everything they touch. It is a bit like wet sugar. When it dries, it gets sticky and can glue a spoon to a saucer. Cement works on the same principle, only much stronger. The cement crystals coat the stones and grains of sand, bonding them into a single mass. And like modern cements, the Roman pozzolana absorbed water during the crystallization process, which is why it could set underwater. The strength of concrete depends not only on the cement, but also on the stones and sand inside it. Stones of different sizes pack tightly together. Small ones fill the gaps between large ones. Even smaller ones fill the remaining spaces, and cement bonds it all. The more tightly packed the mixture, the stronger the concrete. The Romans quickly realized that concrete was a fantastic building material, and its main advantage was that you could make it on site. Stone has to be quarried and hauled to the construction site, sometimes for dozens of miles. That is expensive, heavy, and slow. But concrete can be made from local sand, local gravel, and imported cement. Mix it in a bucket with water, and you have a material nearly as strong as stone. But you can shape it however you want. Pour it into a mold, and it hardens into exactly the form you need. Block, column, vault, wall, anything. The amphitheatre at Pozzuoli, begun under Nero and completed just before the famous eruption of Vesuvius in 79 AD, gives an excellent example of Roman concrete use. At first glance, it looks as though the entire building is made of brick and stone. But that is deceptive. The brick and stone are mostly just a facing. The walls are actually concrete, with brick or stone cladding on the outside and inside. The bricks served as a temporary form, holding the wet concrete from spreading until it set. After that, the whole structure worked as a single concrete monolith. The Romans used concrete everywhere, in walls, foundations, vaults, domes. They realized their new concrete could span spaces. Domes and vaults made of concrete were less expensive and simpler to build than stone ones. To build a concrete vault, you erected a wooden form underneath and poured or placed concrete on top. The formwork had to be very strong because it carried the full weight of the roof until the concrete set. Sometimes, if the wooden planks were not perfectly smooth, they left imprint lines in the ceiling, marks showing where the boards had been. These traces are visible in some Roman structures to this day. But because concrete can be molded, it was often hidden behind decorative stone or brick facing. Because of this, the true scale of Roman concrete use remained underappreciated for a long time. Many people still think the great Roman buildings are made of stone. In reality, a huge portion of those buildings is concrete with a stone skin. Perhaps the greatest advantage of concrete over earlier building materials was logistics. All you had to do was bring the loose materials to the site and mix them with water. The cost of hauling materials over long distances, stone from a quarry for instance, can be enormous. If you can use local sand and local gravel, mix them in a bucket, and get a material nearly as strong as stone in any shape you want, that is concrete. And that is what makes it so revolutionary. The Roman process of making concrete was not bettered until the 19th century, when a deeper understanding of chemistry allowed modern cements to be developed. But the principles of modern concrete are exactly the same. So the Romans discovered concrete, brought it to a high level of quality, and used it to build impressive structures across the empire. But then the Roman Empire fell, and for over 1,000 years, the technology of pozzolanic concrete was essentially forgotten. Medieval builders went back to stone and brick. It was only in the 19th century, when chemists finally understood what happens when cement sets, that a new age of concrete began. This time with one critical improvement. Remember, we said that stone is strong in compression, but weak in tension. Concrete behaves exactly the same way. You can squeeze it as much as you like, and it holds. But pull on it, and it cracks. In an arch or a dome, this is not a problem, because all the concrete is in compression. But if you want to make a concrete beam, a horizontal member resting on two supports and carrying a load in the middle, then the bottom surface of the beam will stretch, and the concrete there will crack, just as stone would. The solution that appeared in the second half of the 19th century was brilliantly simple. Inside the concrete, in the places where it would be stretched, iron bars were embedded. Iron handles tension beautifully. Concrete handles compression beautifully. Together they form a composite material that is strong in both compression and tension, far stronger and stiffer than either one alone. We know this material as reinforced concrete. A key point. If the steel reinforcement is embedded deep enough inside the concrete protects the steel from contact with air and water. The steel does not rust and keeps its strength for decades. On a broken piece of old reinforced concrete, you can see steel bars sticking out. In open air, they are covered in rust, but inside, in the body of the concrete, they are in perfect condition, like new. The arrival of reinforced concrete opened up entirely new possibilities for building, and one of the most impressive examples of what this material can do stands in Brest, in northern France. The Pont de Plougastel. 3 enormous concrete arches, each spanning 620 feet, thrown across the estuary of the Olorne River. The bridge was completed in 1930, and at the time it broke every record for concrete bridges. It was built by Eugène Freycinet, a brilliant French engineer and one of the pioneers of reinforced concrete. Before this bridge, people simply did not believe you could build a concrete bridge that large. Freycinet argued that a concrete bridge would be cheaper and lighter than a steel one, and he was convinced the concrete would be strong enough. By the 1920s, Freycinet had learned to compact his mixture of stone, sand, cement and water to the point where he got concrete with a strength of up to 50 newtons per square millimeter. That is comparable to some types of rock, and more than double what had been possible at the start of the century. The construction process was an outstanding engineering achievement in itself. Freycinet designed a huge wooden arch resting on concrete pontoons. The pontoons could be floated out to the middle of the river, and the wooden arch served as formwork, a mould on which the concrete was placed. The arches were built one at a time. Concrete was placed from both sides at once, 2 halves of the arch rising toward each other but not meeting. Freycinet left a gap at the top and waited for the concrete to harden. Then, using hydraulic jacks, he lifted the arch, literally pushed the 2 halves apart at the top, and set it into its final position. After that, he filled the gap, built the vertical supports, and laid the deck. Inside one of the arches you can see how the structure works. The arch curves downward, growing steeper as it approaches the base. It is a hollow box section, 2 layers of concrete separated by empty space. A hollow structure is lighter than a solid one, but retains stiffness, just as a hollow steel tube is stiffer than a solid rod of the same weight. Triangular elements where the vertical supports meet the arch distribute the load, and provide extra rigidity. Freycinet was not just a builder, he was a scientist. He understood that the strength of concrete depends not only on the mix, but also on how well it is compacted. The more thoroughly concrete is packed, the fewer air bubbles it contains, the tighter the contact between particles, and the stronger the result. Freycinet developed vibration compaction methods that squeezed the maximum strength out of concrete. These methods are still used on every construction site in the world where concrete is poured. After the Plougastel Bridge, Freycinet also observed that concrete slowly deforms, creeps, under sustained load. He realized that if you pre-compress the concrete with tension steel cables before the load was applied, you could compensate for both creep and tensile forces. And so the technology of pre-stressed concrete was born, yet another leap forward in what a building material could do. The principle of pre-stressing is simple. Imagine a stack of books on a table. If you just set them on top of one another, the stack is unstable. The books slide apart easily. But if you squeeze the stack between your palms, press the books together, the stack becomes rigid. You can tilt it, turn it over. The books will not slide, because the friction created by your squeezing holds them in place. Pre-stressed concrete works the same way. Steel cables threaded through a concrete element are tensioned and anchored at the ends. They squeeze the concrete, so that even when a load tries to stretch the concrete, the internal compression cancels out the tension, and the concrete never cracks. The Pont de Plougastel was a turning point in the use of reinforced concrete. It proved that concrete was capable of things previously thought possible only for steel. After nearly 70 years of service, the bridge began to age. In places, water seeped along tiny cracks and reached the reinforcement, which rusted, expanded, and spalled off chunks of concrete. It does not look great, but it is not critical to the structure. In the 1980s, a new cable-stayed bridge was built nearby for motor traffic, and the old Plougastel Bridge was left for pedestrians and cyclists. But it still stands. A bold, confident design, a magnificent expression of the engineering spirit. But concrete, even reinforced with steel, can do something more than bridges and buildings. In the hands of a master, it becomes an artistic medium. The Satolas TGV railway station at Lyon Airport in France is the work of the architect-engineer Santiago Calatrava. Born in Valencia, Calatrava studied sculpture alongside architecture and later turned to civil engineering. In a relatively short career, he became known for outstanding designs of buildings and bridges, structures that blend the functional with the aesthetic and have sculptural qualities. The Satolas station is a prestigious building that cost nearly £15 million. It straddles the main access road to the airport, which runs straight through it. The complex forms a strategic transport hub for the whole region: airport, highway, railway line with high-speed TGV trains running at nearly 190 miles per hour. Approaching the building, you immediately understand why it has become so well known. There is an extraordinary quality to it, a feeling of dynamism and movement, almost of uplift. The whiteness of the concrete mix makes it look like a skeleton fused onto its foundations. Unpainted white concrete ribs arch over the platforms, like the vaulted roof of a Gothic cathedral. But with openings that create dazzling patterns of light and shadow on the floor. In the age of steam trains, nobody would have built a white station. But in the age of electric traction, why not? The curved shape of the roof, and especially the tapering props on either side, precisely reflect the forces at work. They are thicker at the top, where bending forces are greatest. This is what people call the organic quality of the design. Form follows force. not fashion. Concrete here is not just a building material. It is an artistic medium. Railings, details, surfaces, all finished with impeccable craftsmanship. You can see the true nature of concrete, reconstituted stone. Calatrava is a master of elegant structure, blending art, architecture, and engineering. With the Satolas station, he created shapes of great beauty from a material we most often associate with plain, functional buildings. Taking stone and fusing it together with cement was an ingenious idea. Adding steel reinforcement created an incredibly versatile material. And making it beautiful, that is art. So concrete has come a long way, from volcanic sand beneath Vesuvius to the record-breaking bridges of Freycinet and the sculptural stations of Calatrava. Stone, brick, concrete, all of these materials work beautifully in compression. Arches, vaults, domes, all of these structures are designed so that every element is squeezed. But what if you need a structure that works differently? What if you need something tall, light, airy? A structure where the material works not just in compression, but in tension, in bending, in twisting. What if you need to build a bridge across a gorge 400 feet deep, or a tower that rises 1,000 feet? For that, you need a different material. A material equally strong in compression and tension. A material you can draw into thin rods and angles, assemble into lightweight lattice structures, and still carry enormous loads. In the 19th century, that material appeared, and one man, more than anyone else, showed the world what it could do. Alexandre Gustave Eiffel was born in Dijon in 1832. He trained as a chemist, but a twist of fate drew him into the booming railway industry. The 19th century was the age of the Industrial Revolution, and railways were its bloodstream. Tracks were laid through valleys, gorges, mountain passes, and every obstacle needed a bridge or a viaduct. It was in building bridges and viaducts that Eiffel made his name. And that reputation won him the contract that changed his career. A bridge across the gorge at Garabit. The Garabit Viaduct stands in the heart of France, in the rugged Cantal region. It was Eiffel's finest bridge design, a structure built with mathematical precision. An 1,850-foot-long railway deck is carried by an enormous arch spanning the gorge of the Truyère River. The deck stands 400 feet above the bottom of the gorge, and the entire bridge is made of wrought iron. This is where we need to stop and talk about the material, because the arrival of iron and steel in the 19th century radically changed the nature of engineering. Stone is strong in compression, but weak in tension. We already know this. Wood is stronger in tension than stone, but it burns and rots. And iron? Iron is strong in both compression and tension. You can draw it into thin rods, fasten them with rivets, assemble them into lattice structures, trusses, that are incredibly light for their strength. Mass production of iron and steel in the 19th century gave engineers a material their predecessors could only have dreamed of. Eiffel chose puddled wrought iron for the Garabit viaduct, not steel, which was already known at the time. Steel was a relatively new material, and Eiffel preferred what he knew best and trusted. He had an excellent and reliable supplier of top-quality iron in the foundries of Lorraine. The quality of the material was critical. His entire reputation depended on the project's success. Now, how does a truss work? This is a key concept, because trusses were Eiffel's primary building element. In essence, A truss is a beam assembled from individual bars. Take two horizontal bars, a top one and a bottom one, and connect them with a zigzag of diagonal bars. There is your truss. When a load acts on a truss, the weight of a train, say, the truss behaves like a beam trying to bend. The top chord compresses, the bottom chord stretches, and the diagonal bars between them work alternately in compression and tension, depending on direction. One of their key functions is to keep the top and bottom chords in position, preventing them from moving closer together or farther apart. The stiffness of the entire bridge depends largely on the distance between the top and bottom chords, the depth of the truss. The greater the distance, the stiffer the structure. That is why bridge trusses are often very deep, many feet tall. The beauty of the truss is its simplicity. Each bar carries exactly one type of force, either compression or tension, nothing extra. An engineer can calculate the force in each bar and size its cross-section precisely to that load. A thin bar where the load is small, a thick one where it is large. Material is used with maximum efficiency. No ballast, no dead weight. And here is something fundamentally important. A truss is a structure an engineer can analyze. Remember the medieval masons who built by geometric rules without understanding the actual forces in their buildings. With a truss, the situation is completely different. A 19th century engineer could take a drawing of a truss and compute the exact force in each bar, on paper, using statics and trigonometry. No computers, no complex software, just pencil, paper, and a knowledge of mechanics. Eiffel and his engineers did not have access to the complex computational methods available today, so they designed structures they knew how to analyze. The truss was the ideal element, simple, reliable, analyzable, and usable in nearly any situation. The entire Garabit viaduct, from the arch to the supporting piers to the deck, is built from trusses. Giant trusses for the main elements, with smaller trusses inside, working on the same principle. A structure within a structure. Life-size Meccano. All parts were prefabricated at the factory, pre-assembled, all rivet holes pre-drilled. Then the parts were brought to the site and connected with rivets. Riveting was skilled work. You had to heat the rivet red hot, push it into the matching holes, and hammer it flat. At that height, above a gorge, it took nerve and dexterity. But riveting is an excellent joining method. The rust that eventually forms around rivets actually helps. It almost welds the connection together, making it even stronger. One thing that worried Eiffel greatly was wind. The Garabit Gorge acts like a wind tunnel. Wind accelerates through the narrow throat and slams into the bridge with enormous force. Eiffel ran experiments to determine the wind resistance of different types of trusses right on site, on the Great Arch and on the supporting piers. Look at the viaduct's piers. They flare out at the bottom, taking on a pyramid shape. This gives the bridge the lateral stiffness needed to resist the fierce winds that funnel through the gorge. The method of building the arch was ingenious and required no scaffolding below. In a gorge 400 feet deep, that would have been practically impossible. Instead, Eiffel built each half of the arch as a cantilever from the concrete abutments on the slopes, upward and inward, held in place by steel cables anchored to piers on either side. The two halves grew toward each other. The operation demanded extraordinary precision. In a traditional stone arch bridge, the weight from the deck is carried down to the arch through spandrels, those solid stone infills we saw at the Pont du Gard. But here, solid spandrels would have been so enormous that Eiffel's engineers concluded the forces in them would have been impossible to calculate. So they abandoned spandrels altogether and instead used a deep truss bent into the shape of an arch to give the bridge the stiffness it needed to carry trains. A brilliant hybrid. The truss gave predictability of analysis, and the arch shape gave efficient load transfer. And when the two halves of the arch finally met in the middle, only the smallest adjustment was needed. After the arch locked, the deck was laid on top. Eiffel calculated that under the weight of a train, the center of the arch would deflect just 1/3 of an inch. And he was proved exactly right. With the completion of the viaduct, Eiffel's reputation as one of the greatest civil engineers of his time was beyond dispute. The viaduct was functional, like all of Eiffel's previous work. A working bridge, a simple, efficient structure. But Eiffel must have wondered, how far could you go with this technology? The answer came from Paris. Paris, at the end of the 19th century, was the second largest city in the world. A city of wealth, a city of empire. The centenary of the French Revolution of 1789 was approaching, and France wanted to celebrate its new global status. A universal exposition of industry and commerce was announced. A grand exhibition that needed a centerpiece, something that would become the symbol of the exposition and of France itself. The invention of the elevator and the first skyscrapers in America must have inspired Eiffel. He seized the chance to build a huge, lasting monument, the Eiffel Tower. We usually see the Eiffel Tower from a distance, on postcards, in photographs. And only when you stand right underneath it do you truly realize its scale. The feeling of space under those great symmetrical legs is extraordinary. Although Eiffel is inseparably linked to the tower in the public mind, the original concept actually belonged to two of his engineers, Maurice Koechler and Émile Nouguier, who had sketched out a scheme for a super-tall tower as early as 1884. They were all really railway engineers, and they used the techniques they knew best. The tower most resembles a giant railway pier, the exact same principle as the Garabit Viaduct, only stretched vertically to the sky. 250 workers built the tower. Eiffel's engineers produced over 5,300 drawings of every component. As at Garabit, everything was prefabricated, all holes pre-drilled. Parts were brought to the site, lifted by cranes, and riveted together. The weight of iron in the structure is 7,300 tons. With elevators and other equipment, over 10,000 tons. Eiffel chose puddled wrought iron, not steel, for the same reason as at Garabit. He trusted the material and knew its properties. Now, the shape. The famous curved legs of the Eiffel Tower are not just decoration. They are an engineering solution dictated by wind loading. Wind is one of the main enemies of tall structures. It pushes on the side of the tower and tries to topple it, just as if the tower were fixed to a wall horizontally and its own weight were trying to bend it down. The most obvious way to resist wind would be to make the legs straight or angled and brace them to the ground. But the curved shape of the tower's legs does something far more elegant. Each leg is essentially half an arch. It carries the wind load directly down to the foundation along a curve, the way an arch carries weight down along its arc. No bracing needed. The shape does the work. Under each of the 4 legs is a stone base, concealing the foundation structure. Inside, 16 ribs each sit in an iron shoe, resting on a concrete base. Each shoe carries a weight of over 600 tons. The iron in the shoe is 4 to 6 inches thick. During construction, each rib was bolted to the foundation to prevent it from toppling as the structure rose. And hydraulic jacks inside the shoes allowed the structure to be aligned with absolute precision. Eiffel struck a deal with the city that was both commercial genius and enormous risk. He personally invested 5 of the 6 million francs needed for construction. In return, he would keep revenues from visitors during the exposition and for 20 years after. It was the biggest financial gamble of his life, and to ensure a profit, he had to keep costs under control. One way was standardization. Looking up the tower from the first level to the second and beyond, you can see that many of the lattice girders are identical. These are factory-made parts, mass-produced. Standardization saved money on both manufacture and assembly. Every worker knew how to handle a standard part. Under each main floor level are huge girders spanning across the tower, tying the legs together. These create the distinctive gaps in the lower levels, the very openings that make the tower's silhouette so recognizable. Eiffel was very interested in scientific experiments, and one of his justifications for the tower was the study of the lower atmosphere. At the top he had an office, and a wax figure of Eiffel still sits in that office, receiving imaginary guests. For a Parisian in 1889, the highest place you would ever have been was the 7th floor of an apartment building, those same buildings visible below from the tower's first level. Riding the elevator, itself a recent invention, must have been a staggering experience. One of the most interesting engineering facts about the tower is its precision. Despite the grand scale, over 1,000 feet tall, 10,000 tons, the tower was built with the accuracy of a jeweler. Every element manufactured in the factory fitted its counterpart on site without adjustment. Every rivet hole drilled at the factory matched the hole in the mating part. That speaks to the quality of the drawings, over 5,300, and the quality of factory control. In an era when everything was done by hand, that level of precision was an outstanding achievement. After the Eiffel Tower, Paris continued to build and cement its reputation as a city unafraid of bold architecture. Iron gave way to steel, and after steel came concrete, glass, and synthetic fabrics, the materials of the modern city. But Eiffel's tower remained the benchmark, a monument to an era when engineering became public spectacle. Before Eiffel, engineered structures were utilitarian: bridges, aqueducts, factories. Eiffel showed that an engineered structure could be a monument, a symbol, an object of national pride. The tower served no practical purpose, aside from Eiffel's scientific experiments at the top. It existed for its own sake, as a demonstration of what engineering could do. And that is what made it immortal. One more thing about the tower that connects to our main theme, the journey of force downward. On a windless day, gravity, 10,000 tons, travels down the 4 legs, through 16 ribs, through the iron shoes, through the concrete foundations, into the ground. The path is straight and predictable, but when the wind blows, and in Paris it blows often, the situation changes. Wind loading on such an enormous structure is colossal. It tries to topple the tower, and this creates additional pressure on the downwind legs, while lifting pressure off the upwind ones. In the strongest storm, the upwind side of the foundation may actually experience tension, an upward pull. That is what those bolts securing the ribs to the shoes are for. Under normal conditions, the tower simply pushes down on them. In a storm, it tries to pull free, and the bolts hold it in place. The top of the tower sways in strong wind, by a few inches. That is normal. Any tall structure needs a certain flexibility, a give, to spring under wind loading. A perfectly rigid structure would snap, the way a dry branch snaps. A flexible one bends and springs back, like a living tree. Eiffel knew this. His tower is not a rigid pole, but an elastic structure that responds to wind and adapts to it. Iron was only the beginning. After it came steel, stronger, more predictable, more versatile. And steel, combined with concrete, glass, and new fabrics, would open doors to structures Eiffel could not have imagined. Iron and steel opened the door to structures that were impossible in stone or concrete. But the most astonishing results came when engineers learned to combine materials, steel and concrete, cables and fabric, creating structures that seem impossible. Remember Brunelleschi's dome, 13 feet thick, 25,000 tons. Let us see what happened to the dome when engineers started using reinforced concrete and steel instead of stone and brick. In the La Défense district of Paris stands a building that at first glance has nothing in common with Brunelleschi's dome. The Centre des Nouvelles Industries et Technologies, or CNIT, was an exhibition space built in the late 1950s to showcase French industrial achievement. Later, it was converted into a retail centre. But it is the roof that interests us. The roof of the CNIT is, in essence, a dome. Not round like classical domes, but triangular in plan. 3 sides, 3 corners. The weight of the roof gathers along the curved surfaces and is channeled to 3 corners, where it passes into massive foundations buried in the ground. The span of each side is 715 feet, the height 164 feet. And here is the astonishing part. The roof of the CNIT, like Brunelleschi's dome, has a double shell, inner and outer, but they are incomparably thinner. They are made of reinforced concrete. At the base, their thickness is about 2 feet. At the very top, just 2.5 inches. Proportional to its span, thinner than an eggshell. The glass and steel walls around the CNIT carry no load at all. They were added during a renovation in 1988, purely for aesthetics and weather protection. All the load goes through the concrete roof shell, down along curved panels to the 3 corners. How can such a thin shell carry load across such a span? The answer is curvature. If you take a flat sheet of paper and try to compress it, it immediately buckles and loses its shape. Flat, thin panels are catastrophically unstable. But if you give that same sheet a curve, bend it into an arc, it becomes much stronger. Try compressing the bent sheet. It resists far more effectively. A curved surface distributes the load more efficiently and resists buckling. That is the principle used in the CNIT roof. The panels are thin but curved, and curvature makes them strong. Between the upper and lower shells run stiffening ribs from apex to corners. Together with cross walls, they form a honeycomb structure, extremely stiff yet lightweight. The engineer who found the solution for this roof was Nicolas Esquian. As with Brunelleschi, persuading people the structure would stand was a feat in itself, even in the technologically advanced 1950s. Now, let us take one more step and look at a dome that works in a completely different way from anything we have seen so far. The Millennium Dome in Greenwich, London, is the largest dome in the world. 1,050 feet across, with a perimeter of over half a mile. It looks nothing like the domes we have been discussing. It is very thin. It seems to hang in mid-air, held by a web of steel cables. And the forces inside it work in the opposite direction. In every previous dome, in Florence, in Paris, the shell works in compression. Weight pushes from top to bottom, and the shell transfers it to the supports. The Millennium Dome is the reverse. Its shell works in tension. It does not push down. It hangs from above. It is, essentially, a giant tent. 12 steel masts, each 100 meters tall, hold a system of cables. From a central ring at the top, radial cables, stringers, spread outward, tensioned to 2/3 of their braking load, at 40 tons in each cable. Fabric panels of glass fiber coated in Teflon hang from the cables. The thickness of those panels, 1/25 of an inch. 1/25 of an inch. Compare that to the 13 feet of Brunelleschi's dome. A ratio of 4,000 to 1. Materials and technology changed so radically that we went from a stone monolith weighing 25,000 tons to fabric a fraction of an inch thick, suspended on cables. The central ring at the top is a critical element. All the cables pull it outward, and it must withstand that tension. For protection against catastrophic failure, the ring is made of 12 intertwined cables, so that if one breaks, the others take the load. And below, at the base of each mast, massive concrete foundations serve as giant tent pegs. The Millennium Dome is a structure that could not have been built without steel for the masts and cables, concrete for the foundations, and synthetic fabrics for the shell. All the materials we have talked about, stone, iron, concrete, converge here. Domes have always been about communal space, about bringing people together. Their shape inspires awe and a feeling of shelter. That is why we have been building them for thousands of years and making them bigger. And one more structure that beautifully closes the story of the arch. The very arch we started with at the Pont de Gare. In Hamburg stands the Lufthansa hangar, one of the largest aircraft hangars in the world. It holds 3 planes, including 2 Boeing 747s. A jumbo jet is a 7-story building, but it looks small under this roof. Lufthansa wanted the entire front of the building to open for getting planes in and out. Height was limited by airport regulations. The solution? 2 enormous steel arches carrying the front section of the roof. The roof hangs from the arches on hangers, like the deck of a suspension bridge. The arches span 590 feet. And here is what is especially interesting. This arch is far longer and flatter than the semicircular arch at the Pont de Gare or the pointed arch at Cologne Cathedral. And it has no buttresses outside the building. How does it stand? The arch works like a bow, and the roof frame works like a bowstring, pulling the ends of the bow together. Lateral thrust, the very force that has haunted builders since Roman times, is here countered not by massive supports, but by a steel tie running through the entire building. The bowstring effect. The arch sits on flat bearings with no buttresses at all. The entire roof, plus arches, weighs 2,800 tons, the weight of 18 empty Boeing 747s. It was built on the ground beside the building, while foundations were laid on site. Then the roof was slid on rails into position and lifted by hydraulic jacks. Saved time, saved money, and far safer than assembling everything at height. The arch here, as at the Pont du Gard, as in Cologne, as at Garrabee, draws its strength from its shape. That shape has evolved over centuries as new materials appeared and our understanding deepened. The arch has a glorious past and a great future. From a stone semicircle laid on wooden centering, to a steel curve spanning 590 feet without a single buttress. From a dome 13 feet thick, to fabric a fraction of an inch. Every step along this path is a new material, a new calculation, a new form. But the principle stays the same. Find the shape that sends forces where they need to go, and the structure stands. Now let us return to the ground, literally, because every structure we have talked about so far stands on the ground. And until now, we have taken the ground for granted, a solid surface you can lean on. But the ground is not always a reliable partner. Sometimes it is soft. Sometimes it shifts. Sometimes it lets you down, slowly, invisibly, over centuries. And one of the most famous structures in the world is living proof. Pisa, a city on the west coast of Italy that in the Middle Ages was a wealthy and powerful maritime republic. The sea was much closer to the city then than it is now, and Pisa thrived on trade and its navy. And as befits an ambitious medieval city, Pisa built a great cathedral, a baptistry, an ossuary, an entire complex of religious buildings, and among them, a bell tower, a campanile, meant to be one of the tallest in the country, calling the citizens to prayer. Construction of the tower began in 1173. Bonanno Pisano laid the foundation and began raising the walls. The tower was conceived as a hollow cylinder with a spiral staircase inside leading up to the bells, a height of 180 feet, both inner and outer surfaces clad in white marble. And here is what happened. Records suggest the tower began to lean as soon as the first floor was completed. The reason is the ground beneath the tower. The soil here is soft clay, easily compressible and sensitive to changes in groundwater level. And the water level depends on the sea, on the river, and crucially, on the construction going on nearby. In particular, the recently built cathedral, whose enormous weight changed the pressure in the soil. Building a tower on that clay was like building a tower of blocks on a soft mattress. By the time construction reached the fourth floor, the tower weighed about 10,000 tons, and one side had sunk 20 inches relative to the other. In 1178, just 5 years after the start, construction stopped. Partly because the Pisans had to fight Genoa, but the pause, it turned out later, was a lifesaver. Over 100 years of forced interruption, the clay under the foundation, consolidated under the weight of the already built floors, grew stiffer, and this actually stabilized the tower enough for construction to continue. In 1272, Giovanni di Simone resumed work. 6 more years of building, another 4,000 tons, and the south side had sunk nearly 3 feet. But the builders kept going. The bell chamber was finally added between 1360 and 1370. And here is a telling detail. To make the bells hang straight, the bell chamber had to be perfectly level. So on the overhanging south side, 6 steps lead up from the base to the bell chamber. On the opposite side, just 4. That is what gives the upper part of the tower its distinctive curved shape, as though the tower were trying to straighten itself. Walking the staircase inside the leaning tower is a strange experience. On the south side, the stairs seem to lean away from you. The steps recede into the distance. Then you turn the corner, come out on the north side, and the staircase is nearly vertical, steep, looming. The contrast is physical, and it never lets you forget that you are inside a structure that has deviated from the vertical by several feet. Over centuries, as the tower continued to lean and sink, it pushed up a mound of earth on the south side, which paradoxically helped slow the movement. But in the 1830s, and this is an astonishing story, someone decided it would look nice to reveal the stonework at the base and dug that mound away, after which the rate of lean increased dramatically. By removing the natural prop the tower had built for itself over centuries, they accelerated the very process they were trying to control. By 1990, the tower was declared unsafe and closed to visitors. By then, the lean was about 15 feet from the vertical. The tilt was increasing constantly, and in the early 1990s, it was discovered that the tower was also rotating. The Italian government finally committed to action, after the collapse of a civic tower in Pavia, which served as a wake-up call. The first step was temporary stabilization. Tons of lead weights were hung on the north side of the foundation as a counterweight. But a permanent solution was needed, and the solution that was chosen turned out to be elegant and simple. It did not even require touching the tower itself. Engineers began extracting small volumes of soil from beneath the north side of the foundation, drilling down from various points. The soil was left with tiny cylindrical cavities, and these immediately squeezed shut under the tower's weight. The soil compacted, the surface settled slightly, and the tower, slowly and in a controlled manner, tilted back toward the north. By choosing exactly where to extract soil, the engineers could literally steer the tower. Think about how beautiful that is. No props, no jacks, no contact with the structure itself. You just remove a little earth from one side, and an 800-year-old tower weighing 14,000 tons begins to move in the direction you want. The goal is to reduce the lean by 1/2 degree. That is just about 20 inches at the top. Of course, nobody is planning to straighten the tower completely. After all, the lean is what brings the tourists. If the tower stood straight, it would be just another beautiful medieval bell tower. With the lean, it is unique. The engineers aim to make the tower safe for another 2 or 3 centuries while keeping it leaning. Here it is worth returning to our main theme, the journey of force downward. In the Leaning Tower of Pisa, that journey went wrong. Gravity pulled the tower down, and the foundation was supposed to transfer that weight into the soil evenly. But the soil turned out to be uneven, one side softer than the other. And the force, instead of going straight down, began to slide, one side of the foundation sinking faster than the other. The tower tilted, and the tilt, in turn, shifted the center of gravity. Now, more weight pressed on the southern, sunken side, which accelerated the sinking. A vicious circle. Note: the tower itself is structurally sound. The masonry is incredibly strong. Stones have shifted in places, cracks have opened and closed again, corners have chipped off from compression. But the structural integrity is intact. The problem is not the structure. It is the foundation. More precisely, what is underneath the foundation. The tower is a perfect example of how even an impeccably built structure is helpless if the ground is not right for it. The medieval masons must have been in awe of their moving tower, not understanding the subtle processes happening in the clay beneath the foundation. They considered the lean a miracle, a sign that God was on Pisa's side in the wars with Genoa, a sacred relic, a place of pilgrimage. Pisa lost the war, but its tower secured the city's place in history forever. Now, imagine wanting to build a leaning building deliberately. Not by accident, as in Pisa, but on purpose, by design. Sounds crazy? In Madrid, that is exactly what they did. The Torres Puerta de Europa, Gateway to Europe, are two enormous black towers looming over the main road north out of the city. Each leans 3 times more than the Leaning Tower of Pisa, and they are twice as tall. 26-story office buildings, one occupied by one of Spain's major banks. For an engineer, these structures are simply unique. They look impossible, those huge black masses hanging over the road. A powerful, almost aggressive architectural statement. But it is not just showmanship. The lean has a practical reason. During planning, site restrictions required the towers to be 460 feet apart at the base, and if they had been ordinary vertical buildings, they would have been visually lost at that distance. The architect decided to lean them toward each other, creating a visual link, a gateway. A bit of a stunt, but it works. The towers truly dominate the entire space. Leaning buildings are very rare, and they require special engineering solutions. But the principles are simple. The most critical question is the most obvious. How do you stop them from tipping over? The overhanging upper floors want to tip the building forward. The simplest solution is to weigh it down at the back, in the foundation. Below each basement sits 14,000 tons of concrete, performing exactly the same role as the lead weights on the Leaning Tower of Pisa. A counterweight, offsetting the lean. 14,000 tons, enough concrete to cover the entire base area over 30 feet deep. But the counterweight prevents tipping, what prevents bending and sagging. Every building must be stiff enough to hold its shape. In a leaning building, that problem is many times worse. The steel and concrete frame must work as a rigid skeleton, and the shape of that frame is critical. The silver triangular elements clearly visible on the sides of the towers are not decoration. They give the building its primary stiffness. Why the triangle? Take a napkin and draw 2 shapes, a triangle and a square. Now imagine pressing on the corners. The square collapses easily. It turns into a diamond, a parallelogram. Its sides fold like a hinged mechanism. The triangle does not. None of its sides can move because the other 2 hold it in place. The triangle is the most stable geometric shape. It is rigid by definition. That is why triangular elements appear so often in building structures, from Eiffel's trusses to the frames of the Madrid towers. Along the back of each building, from top to bottom, run steel cables. Imagine your arm is the building. If you stretch a rubber band from your fingertips to your wrist along the back of your hand, it pulls your fingers back, straightens and stiffens your arm. The cables in the towers work the same way. During construction, by tightening the cables, the engineers straighten the top of each building by 6 inches. And if needed, that tension can still be adjusted today. This technique is called post-tensioning. Between the top and the bottom of each building is a transition zone. In this space, a massive concrete core runs the full height, carrying the main structural load. This core is the backbone of the building. Here, the elevators are housed. The concrete core is enormous at the base. Think about this building in terms of our main theme, the journey of force downward. In a vertical building, force goes straight down through columns and walls to the foundation. Simple and predictable. But in a leaning building, force does not go vertically. It is offset. The center of gravity of the upper floors is not above the foundation, but in front of it. And that means that in addition to vertical force, a turning moment appears. The building's tendency to topple. 14,000 tons of concrete counterweight offset that moment. Post-tensioning cables add stiffness. Triangular frame elements prevent deformation. Each system solves its own problem, and together they create a building that looks impossible, but stands perfectly, reliably. When the towers were completed in 1996, they instantly became an architectural landmark of Madrid. Keeping a tower standing upright means controlling the forces going down. But what if your tower stands not on soft clay, as in Pisa, and not on city soil, as in Madrid, but on rock, on a mountaintop, battered by winds of over 100 miles an hour? In Barcelona, on Mount Collserola, stands a telecommunications tower built for the 1992 Olympic Games. The Torre de Collserola, 945 feet tall, nearly as high as the Eiffel Tower, on top of a mountain. 13 floors, nearly all for satellite dishes and transmitting equipment. The tower can hold 700 people. Traditional communication towers are usually open steel lattice structures, like power line pylons. But if the new tower had been built that way, it would have needed a huge base, and it would have looked like a giant industrial pole, completely at odds with Barcelona's stylish image. The city saw the new tower as an opportunity for something unusual. British architect Norman Foster won the competition. His design stripped the structure to its minimum. The tower is a simple, hollow, circular concrete shaft. 13 floors wrap around it, held by a system of steel trusses and cable stays. Above the concrete shaft, a 260-foot telescopic steel mast reaches skyward. At the very top sits a small crane for lifting equipment. The foundation is a simple concrete disc, 65 feet across and just 16 feet thick. It does not need to be thicker because the tower stands on rock, not soil. Rock handles load incomparably better than Pisa's clay. But such a tall, thin shaft would be far too flexible without additional reinforcement. So the tower is held by steel cables, like guy ropes on a mast. Wind is the main threat here. The tramontana, a northwesterly wind, rushes over the hills and down the slopes. Gusts can exceed 100 miles an hour. 3 sets of high-strength steel cables are anchored to enormous concrete blocks, 2,000 tons of concrete each. The cables are tensioned so that even in the strongest wind, they will never go slack. And the tower stays rigid. In a 60-mile-an-hour wind, the top floor will shift just 3.5 inches. At the top floor, 155 feet up, inside the concrete shaft, the tower hums quietly. Equipment runs, antennas transmit, and all around, cables, steel frame, concrete shaft, everything carries enormous forces, holding this extraordinary structure in its exact position. Every second, thousands of tons of tension pass through the cables, thousands of tons of compression through the concrete shaft, and everything is in perfect balance. As long as the tramontana blows, and it blows often, the balance of forces continuously shifts, and the tower breathes with the wind like a yacht's sail, never exceeding its design limits. The cables connecting the top of the steel frame to the top of the concrete shaft pass in front of the microwave dishes. If they were steel, they would block the radio signal. So these cables are made of Kevlar, a synthetic fiber as strong as steel but invisible to radio waves. And the floors? They were not built at height. They were assembled on the ground and lifted by hydraulic jacks. 4 days, and the 13-story structure was in place. The Torre de Colserola is an undeniable engineering masterpiece. To make a leaning tower safe for centuries, to break every convention in Madrid, to combine beauty with function here in Barcelona, all of it took extraordinary ingenuity. But all of these structures are on land, on solid ground or on rock. They exist in a world where air surrounds them, wind is the main opponent, and the earth beneath them is a reliable ally. Well, most of the time. What if you need to build something where there is no land? Where beneath you lies 1,000 feet of freezing water, where storm waves batter the structure 5 million times a year, where wind, currents and salt water destroy everything they touch. For that, you need to go to sea. And when you go to sea, the rules of the game change completely. Plymouth is a historic naval city and fishing harbour in the southwest of England. It stands at the entrance to the English Channel, in one of the most exposed corners of Britain. So it is no surprise that for centuries, treacherous approaches to Plymouth have been protected by lighthouses. And we need to visit one of the most famous spots, the Eddystone Reef, 14 miles out in open water. Since 1699, there had been a lighthouse on this reef, but the ferocity of the weather in the channel claimed 3 of them. One was literally swallowed by the sea during the worst storm in British history, in 1703. The first lighthouses were built of wood. Their builders believed wood was better because it was flexible. It could spring under the impact of waves. But wooden lighthouses were either washed away or burned down. John Smeaton's lighthouse, built in the 1750s, was far more successful. And the reason for its success lies in several fundamental engineering decisions, each worth examining. Smeaton proposed building from stone, from granite, dense and resistant to weathering. He based the shape of the lighthouse, he said, on an oak tree. "My main aim," Smeaton wrote, "is to construct a tower whose every part should be strong in direct proportion to the stress it is likely to bear. A wide base tapering upward, like a tree trunk." But Smeaton's main innovation was not the shape, but the method of joining the stones. He understood that a stone tower standing in the open sea under the impact of storm waves would experience not only compression, but also tension. Waves would try to rip stones from the surface, loosen the masonry, pull blocks apart. Ordinary stonework cannot resist that. So Smeaton developed a system of interlocking stones, complex grooves and projections like pieces of a puzzle, plus iron and marble dowels locking the entire structure into a single monolith. Every stone was locked by its neighbours on all sides. Pulling one out without destroying all the others was impossible. The higher you go in the lighthouse, the thinner the walls. This makes sense. The load on the lower levels is greater. The granite, a type called moorstone, is very dense and resistant to weathering. Building a lighthouse on a reef in the open sea was a feat in itself. Smeaton invented a special crane for lifting heavy stones from a boat moored alongside the rock. Work was only possible in calm weather and at low tide, a few hours a day. Every stone was cut and fitted on shore, numbered and shipped by sea. On the reef, stones were laid in precise order, interlocking with each other like a 3-dimensional puzzle. The slightest error and a stone would not fit. Precision had to be absolute. At the top of the lighthouse was the lantern room, where keepers maintained the flame. A frame with holes for 24 candles. Smeaton's lighthouse was completed in 1759 after 3 years of construction, and its 24 candles burned in that lantern for over 100 years. During its service, the lighthouse endured force 12 storms. On one occasion, in 1824, the keeper recorded that water came from the top of the building in such quantities that they were overwhelmed. Water came not from the side, but from above, over the very top of the lighthouse, and the structure held. What finally beat Smeaton's lighthouse was not storms or waves. Storms undermined the rock it stood on. By 1877, the foundation, the rock itself, was so damaged by erosion that the lighthouse had to be decommissioned. In recognition of his achievement, the tower was disassembled, stone by stone, shipped to shore, and rebuilt on Plymouth Hoe, where it stands today. Smeaton's lighthouse teaches us an important lesson. A structure can be perfectly designed and flawlessly built, but if the foundation beneath it is not reliable, none of it matters. Smeaton defeated the waves, but lost to the rock. More precisely, lost to what the sea did to the rock over 120 years. Lighthouses have to withstand the blows of the sea, but they cannot hold it back. For that, something else entirely is needed. Something truly grand. Before we turn to sea defense, it is worth remembering that the idea of protection against external forces is far from new. Centuries before the Dutch barriers, Marshal Vaughn, the military engineer of Louis XIV, was solving the same problem. Only his opponent was not waves, but cannonballs. Vaughn was a veteran of many sieges, both as attacker and defender. That unique experience on both sides of the barricade gave him an understanding no other engineer of his time possessed. Louis appointed him to oversee the construction of a network of fortresses across France, over 150 of them. An awesome responsibility that made him one of the most powerful men in the country. At the citadel of Blaye in southwest France, guarding the mouth of the Gironde estuary and the city of Bordeaux, you can see a classic example of his method. The fortress is surrounded by enormous curtain walls with triangular bastions at every corner. Between and in front of the bastions, ravelins, arrowhead-shaped fortifications. Around everything, a great ditch. Beyond the ditch, the glacis, a built-up mound preventing a direct line of fire at the base of the walls. And here is what matters for our story. Behind the walls is earthfill. The walls do not just stand on their own, they hold back a mass of soil. And this creates an entirely new engineering problem. A wall retaining soil must withstand not only its own weight, but also the lateral pressure of the earth. Too thin, and the soil pushes it over. Too thick, and construction becomes prohibitively expensive. Vaughn was the first to fully recognize this problem and propose design solutions. He established a geometric rule. The slope of the wall's face should be 1 to 5 relative to its height. The back, vertical, against the soil. On top of one of the ravelins, the wall at the top is about 3 feet thick. 7 feet below, at the base, the thickness grows to over 8 feet. This trapezoidal profile is the result of Vaughan's rule. Remember heuristics? Vaughan's 1 to 5 rule is a classic heuristic. He did not calculate soil pressure using formulas. Those did not yet exist. He derived the rule from the experience of 50 sieges, from observing which walls stood and which collapsed. and he standardized it across all his fortresses. Blay is one of Vaughn's early works, and it is remarkably well preserved. 500 masons built it over 4 years. The fortress was never taken. Vaughn's fortresses became obsolete when the invention of the howitzer allowed shells to be lobbed over walls from a distance. Today, massive earth defenses are more likely to be defending nations from nature than from armies. But the engineering challenges are every bit as demanding. On the 1st of February, 1953, a massive storm surge struck the coast of the Netherlands. Sea defences were breached in 67 places. 1,800 people drowned. For a country where much of the territory lies below sea level, this was a catastrophe of existential proportions. For centuries, the Dutch had relied on dunes and local dikes for protection from the sea. After 1953, it was clear this was not enough. National survival was at stake. The government decided the entire coastline must be protected by a system of dikes and barriers. The project was called Delta, and it was to become one of the largest and most expensive engineering projects in history. The scale of the Delta project is hard to overstate. This was a decision made by an entire nation to rebuild the coastline in order to survive. The cost was astronomical. The timeline, decades. But the alternative, a repeat of 1953, was too terrible to contemplate. The Dutch decided that the safety of their people was worth any price. And this decision, not an engineering one, but a political one, determined everything that followed. Engineers received a mission and resources. From there, their work began. One of the last and most difficult sections of the Delta project was the estuary of the Eastern Scheldt, the Oosterschelde. The original plan called for a simple dam blocking the estuary, but that would have destroyed the unique ecosystem of the tidal zone. Instead of a dam, the Dutch chose to build a vast barrier with gates that could close in the event of a storm surge and remain open the rest of the time, letting tides flow in and out. Strong currents and shifting sand on the floor of the Eastern Scheldt made construction extremely difficult. The contractors compacted the seabed and laid a vast mattress of stones and sand to create a solid foundation on which to place 65 concrete piers linking the barrier gates over a distance of 2 miles. For almost all their lives, these gates remain open. The sea flows freely in and out of the estuary. But when a storm surge approaches, the gates close. Each 500-ton gate drops into position like a guillotine. Warning of an approaching surge comes hours in advance, but the entire barrier can close in 90 minutes. The barrier does not need to be perfectly watertight. It only has to hold back the surge during high tide. After the tide passes, the danger recedes. Each of the enormous concrete piers is as tall as a 15-story building, but only a quarter is visible above the water. The water here reaches 100 feet deep. The piers are hollow. They were built in giant dry docks, then towed to position and sunk onto the prepared seabed. Construction and installation took over 4 years. At the base of each pier, 18,000 tons of concrete. They are shaped like a gold bar, elongated along the barrier line for stability against storm forces. After installation, each pier was weighted with another 12,000 tons of sand to protect against scour. Stone was imported from as far as Finland and Belgium. 5 million tons of stone went into covering the entire 2-mile length of the barrier. The barrier was completed in 1986. Its cost was a third of the entire Delta project. and 3 times what a simple dam would have cost. But it provided protection for the Dutch while preserving the natural tidal environment of the estuary. Now, from the Eastern Scheldt to Rotterdam, the largest port in Europe. And the problem? How do you protect a city from a storm surge without closing the main waterway through which hundreds of ships pass every day? The solution is a pair of enormous swing gates. In an emergency, the gates float out of dry docks, swing into the shipping channel, and meet in the middle, stopping the sea. The barrier opened in May 1997. The concept is stunningly simple. 2 identical gates, each the size of the Eiffel Tower laid on its side. But they weigh twice as much. Steel walls 72 feet high and 690 feet long. The gates are hollow, so they can be floated into the river like a ship, then filled with water for ballast and sunk to the riverbed, onto a prepared concrete foundation. When the dry dock is empty, and we are lucky that today it is, you can go down and see the structure from below. Beneath the wall, along its entire length, runs a rubber sealing strip. When the gate settles onto the concrete sill at the bottom of the river, this strip compresses under the wall's weight and creates a watertight seal. It sits on pistons that let it adjust slightly, creating a perfect fit. Behind the wall is a massive truss. 8 main struts take most of the force from the sea and carry it along the tubular arms to the foundation on shore. Additional struts above provide rigidity against twisting. And here, one of the most impressive engineering details I have ever seen. The pivot. A ball and socket joint 33 feet across, the largest ball joint in the world, weighing 680 tons. Under storm loading, 35,000 tons of force arrive right here on this sphere. You can go down inside the ball joint, and it is one of the most powerful experiences any engineering structure can offer. You stand inside a steel sphere weighing 680 tons. All around you, smooth steel surface curving away, upward and sideways. 6 hydraulic pistons, the very ones that lift the ball for maintenance, like giant fingers holding a ball. When the gates close, the working face of the ball enters a massive grey socket on shore, and 35,000 tons of storm force pass through that contact. The pressure on the contact surface is the same as a submarine would feel 6,000 feet underwater. And all that pressure is transferred through a steel shoe into the concrete foundation. The entire foundation will give about 8 inches under load, then spring back. Rotterdam's storm surge barrier is engineering on a grand scale. Ingenious in concept, beautifully executed, immaculately maintained. But both structures we have seen, Oosterschelde and Rotterdam, are land-based, even if on the border with the sea. If we truly want to talk about building in the sea, we need to go into open water. Off the coast of Norway, beneath the North Sea, lies Troll, one of the richest oil and gas fields in the world. The challenge? Build a structure that will stand on the deep seabed, withstand ferocious storms, and serve as a platform for gas extraction for over 50 years. We depart from Bergen, Norway, for Troll A gas platform, the tallest concrete offshore platform in the world. The only way out is by helicopter, so a survival suit is required. The Troll field lies 37 miles from the Norwegian coast, and there it is. 4 enormous concrete legs rising from the sea, an incredible sight. The drilling deck and superstructure of Troll A sit on 4 massive concrete legs reaching over 1,000 feet down to the seabed. Each leg is taller than the Eiffel Tower, 1,210 feet. The base of the platform is 19 concrete cells built on land. The base was towed into a deep fjord where the 4 towering legs were added. Each step of assembly was a marvel of precision. The whole structure was sunk deeper in the fjord water, and the platform, the upper part, with the drilling rig and living quarters, was brought in on barges and lowered on top. Water was pumped out of the structure, and it floated up a matter of inches to connect with the platform. After assembly, the entire structure was refloated and towed to the field. The tow took several days and required a fleet of powerful tugboats. Weather had to be perfect. A storm during towing could have been catastrophic. The entire operation was planned with the precision of a military campaign. It was the largest object ever moved across the surface of the Earth. On the helipad, 250 feet above the water, easy to forget that most of the structure is underwater, like an iceberg. At this height, you are level with the top of the Empire State Building. An offshore platform is really a chemical plant at sea. Below, gas processing equipment. In the middle, the drilling rig. 39 wells will be drilled into the seabed, fanning out to a depth of about a mile and reaching out half a mile in every direction from the platform. On average, it takes a month to drill each well. But we are not interested in the gas. We are interested in why this structure stands. For that, we need to go down to the seabed. The journey down, by elevator, inside one of the concrete legs. Silence. Eerie silence. With the sea right outside the wall, the feeling is of being on another planet. On land, you see tall buildings, tunnels, grand structures. But here, in this environment, the scale of engineering and its achievements is truly extraordinary. You feel that there is no place on this planet, or perhaps any other, that we could not reach. The water pressure outside, right behind the wall, is 30 times the air pressure inside. It is trying to crush the leg, to squeeze it. The structure withstands this thanks to 2 factors: the strength of the heavily reinforced concrete and the cylindrical shape, which is the most efficient form for resisting external pressure. The same principle as a submarine hull or an aircraft fuselage. A cylinder distributes pressure evenly around its circumference, and no single point bears a concentrated load. At the very bottom, at the base, the gas pipelines turn the corner and head along the seabed to Norway, 37 miles across the bottom. Underfoot, a concrete floor, and beneath it, marine mud. The entire platform is pressed deep into the seabed. Picture 19 upside-down coffee cups, the walls of each cup driven deep into the mud. If you have ever tried to press a cup into wet sand and then pull it out, you know the force that holds it in place. Suction inside, vacuum. They keep the cup from coming free. That is exactly how the base of Troll A works. 19 hollow chambers pressed into the seabed, held in place by their own weight and the suction effect. At the very bottom, on the concrete wall, there are inscriptions. It might look like graffiti, but it is actually a visitor's book. Everyone who comes down here can sign the wall. At the bottom of the North Sea, inside a structure standing in one of the most hostile places on the planet, a visitor's book. There is something deeply human about that. Among all this concrete power, among thousands of tons of reinforcement and 30 atmospheres of pressure, someone's signature in marker on a wall. A reminder that behind every structure stand people. And somewhere at the bottom, a small leak, dripping from a valve. Nothing serious, just a leaky fitting collecting some water. Even on a platform costing billions, small things happen. Engineering is not perfection. It is sufficient perfection. The structure is designed with a safety margin that accounts for leaks, corrosion, and unforeseen loads. Perfection is unattainable and unnecessary. What is needed is reliability. And reliability means small problems do not grow into big ones. Up on the deck level, the problem is different. Here it is not water pressure, but the impact of waves and wind. On a calm day, it is peaceful, but in a storm, waves can reach the deck, 100 feet above sea level. The deck is high enough to avoid being swamped, and it is securely fastened to the 4 concrete legs, which are strong and stiff enough to withstand an estimated 5 million waves crashing into them every year. Structures like the Troll platform give us the confidence to know that we can live and work alongside the sea, whatever the conditions. It is no longer a question of hiding from the sea. It is about coexisting, on the coast and in the deep ocean. Think about the journey we have made, from a stone laid by a Roman slave onto a wooden centering frame somewhere in the south of France 2,000 years ago, to a concrete cylinder on the floor of the North Sea, withstanding 30 times atmospheric pressure. Every step along this path is an attempt to solve one and the same problem. Take the force that pulls everything toward the ground, or pushes from all sides, or batters with waves, or loads with wind, and guide it through a structure so that nothing breaks. Arch, vault, dome, truss, cable, shell, concrete cylinder. These are all answers to a single question. How do you deliver force to where the ground, or rock, or seabed can absorb it? Shape determines strength. The curved surface of a dome, the arc of an arch, the flare of the Eiffel Tower's legs, the cylinder of a Troll platform leg. All of these are shapes that let forces go where they need to go and keep them from going where they should not. Material matters. Stone, iron, steel, concrete, fiberglass. Each brings its own limitations and possibilities. But it is the shape of the structure that determines whether it stands or falls. And behind every one of those shapes stands a person who made a decision. An engineer who knew, or at least hoped he knew, how the structure would behave. Sometimes he knew precisely, like Eiffel, who calculated the deflection of the Garabit arch to within a fraction of an inch. Sometimes he knew approximately, like the Roman builder following the rule of thumb, that arch stones should be 1/20th of the span. Sometimes he was working blind, like Brunelleschi, who convinced everyone the dome would stand, armed with nothing but a model and faith in his own intuition. But here is what unites them all, from the Roman mason to the Norwegian offshore engineer. And here is what is worth remembering from our entire journey. There is one engineer we have not talked about yet, and his story is perhaps the most eloquent illustration of what engineering really is. Peter Rice, an Irish engineer, one of the most brilliant of his generation. He played a central role in projects as varied as the Louvre Pyramid and the Sydney Opera House. He was invited by the architect Adrian Fainsilber to design 3 massive glass conservatories, the so-called glass houses, in the Paris Museum of Science and Industry, a building in the northeast of the city. The museum is housed in a former industrial building, and inside it stand enormous trusses that look as though they were taken straight from the Eiffel Tower. They are massive even for this building, but that is not why we are here. We are here for the work of Peter Rice. Rice's glass houses are spacious, light structures meant to connect the museum with the park outside, and they represent the pinnacle of refinement in steelwork. They are so light, they seem to lack substance. Next to them, Even the airy structures of the Eiffel Tower and the Garabit Viaduct look bulky. The contrast between the heavy industrial trusses inside the museum and these delicate glass structures is total. And from the engineering perspective, this is what makes the building truly remarkable. Let us take apart how Rice's glass wall works. Glass is actually a very strong material in its pure form, but in practice, it is quite weak and extremely brittle. It breaks in an explosive way when any scratch or defect, even a microscopic one, causes a stress concentration. Remember we said stone is weak in tension? Glass is worse. The slightest surface flaw and it shatters. Steel, on the other hand, can take enormous loads in both tension and compression, and it has a property called ductility. It stretches before it breaks. This gives a warning. The structure deforms before it fails, a sort of alarm signal. I'm about to break, take action. Glass gives no such warning. Rice's challenge was to bring two completely different materials together in a single structure, and the solution he found is remarkable in its thoughtfulness. Each of the three glass houses has 24 steel frames, each holding 16 glass panels 6.5 feet by 6.5 feet. The 16 panels in one frame weigh 2 tons. Carrying that vertical weight and handling the wind load from outside, that is the job of this lightweight steel frame and its connections. Here is how it works. The glass panels hang one from another, and their weight is carried upward, to the top of the frame, where a spring mechanism locks the top panel in place. Gravity pulls down. So the force travels up the chain of panels and from there into the frame. Wind loading is handled entirely separately, through a stainless steel cable forming a flat truss. The two systems are completely independent of each other. They connect only at the tubular steel frame around the perimeter. And here is the detail that makes it all possible. The connection of glass to metal. At each of 5 attachment points, a ball and socket joint. Like a hip joint, a ball inside a cup. The joint allows the glass panels to move independently of each other. The whole system is articulated, hinged. The glass wall can swing inward under a gust of wind, and each panel rotates in its joint without transmitting stress to the next one. The glass does not break because it does not need to carry loads it was not designed for. Each load, weight, and wind is handled by a separate path, a separate system. Rice died in 1992 at the age of 57. In his relatively short life, he created structures that redefined the relationship between engineering and architecture. He proved that the engineer is not just a person who calculates to realize someone else's vision. The engineer is a co-creator. The engineer sees in the material what the architect does not. The engineer understands how force flows through a structure and can turn that understanding into beauty. Compare Rice's glass houses with Eiffel's trusses standing in the same building. The difference is a century of technological progress. Eiffel's trusses are honest, powerful, straightforward. Every bar is visible, every rivet in place. That is the beauty of strength. Rice's glass houses are graceful, weightless, almost immaterial. Every element refined to the limit. That is the beauty of lightness. 2 approaches, 2 centuries, 2 ways of working with material, and both are beautiful, each in its own way. Rice admired 19th century engineers like Eiffel. He spoke of their structures as having a simple honesty that goes straight to the heart of the physical characteristics of the material. But his own work was more Swiss watch than railway pier. Meticulous attention to detail and sophisticated calculations allowed Rice to refine every element. Like a racing yacht, each component has a precisely defined function. No excess baggage. And here is the bitter irony. In a museum dedicated to science and technology, Rice's brilliant and innovative design is not acknowledged or explained anywhere. You walk past those glass walls without knowing who designed them or what engineering thought lies behind them. Engineering is invisible. It works so well that people stop noticing it. Rice believed that the role of the engineer extended beyond calculations and structures. He felt that an engineer should build structures that people warmed to, structures that conveyed a feeling of having been designed by someone who cared. In this, he differed from Eiffel, who built functional, honest, but utilitarian structures. Rice wanted the structure to be beautiful as well, not beauty for its own sake, but because beauty and good engineering, he believed, coincide. A structure in which every element carries exactly the load it was designed for, with not a gram of excess. Such a structure inevitably looks elegant. And you know, there is a deep truth in that. Look at the flying buttress of Cologne Cathedral, at the curved leg of the Eiffel Tower, at Rice's glass joint, at the cable stays of the Torre de Colserola. All of these elements are beautiful, and they are beautiful precisely because their form is dictated by function. Nothing extra, nothing accidental. Every line, every curve, an answer to a specific force. Henry Petroski, the author of To Engineer is Human, writes that engineering is, at its core, applied anxiety, a discipline of imagining failure. An engineer spends a lifetime picturing everything that could go wrong and designing the structure so that none of those scenarios comes to pass. Every successful building, every standing bridge, every working platform is a monument to all the disasters that did not happen, because someone foresaw them and prevented them. And Billy Vaughn Koen adds another layer. An engineer, Koen writes, never has complete information. He always works under uncertainty. The soil under the foundation is unpredictable. The wind is unpredictable. The behavior of a material under extreme loads is not always predictable. The engineer uses the best available solution, what Koen calls state-of-the-art, knowing that this solution is not perfect. It will be surpassed by the next generation, but it is the best available right now. And that is enough. All of them. The medieval mason building Cologne Cathedral by geometric rules he could not explain. Eiffel calculating the deflection of his arch and proving precise to a fraction of an inch. Brunelleschi convincing his clients with a model and intuition. Freycinet raising a concrete arch with hydraulic jacks. Smeaton locking the stones of his lighthouse into a puzzle. The engineers of Troll A pressing concrete cups into the seabed. Peter Rice hanging 6.5 feet of glass on a ball and socket joint. All of them were doing the same thing, making decisions under uncertainty, relying on experience, on calculation, and on what Koen calls heuristics, rules that do not guarantee the right answer, but very likely lead to a good solution. And maybe that is why engineering is so hard to notice. It works quietly. It does its job invisibly. When you walk into a building and feel safe, you do not think, someone calculated that beam. When you drive across a bridge, you do not think, someone checked the fatigue strength of every bolt. When you turn a door handle, you do not think about the fact that this is a small machine, converting the rotational movement of your hand into the linear movement of a latch. The same principle of an inclined plane wound around a cylinder like a bolt. The bolt, by the way, the most common fastener in the world. Its entire job is based on a precisely measured moment of force, torque. When you tighten a bolt with a wrench, you convert rotational effort into a linear clamping force. The bolt stretches slightly, by fractions of a thousandth of an inch, and it is that stretch, that elastic stress in the bolt's shaft, that creates the clamping force holding the connection together. The bolt wants to return to its original length, and that restoring force is your clamp. Roughly 85 to 90% of the torque you apply to a bolt is lost to friction. Friction between the nut and the surface. Friction between the threads. Only 10 to 15% of your effort actually goes into clamping. And that means the relationship between the torque you apply and the actual clamping force is extremely sensitive to friction conditions. A drop of oil on the threads, a different surface roughness, a washer instead of a bare nut, and the clamping force at the same torque setting can change by 30 to 40%. That is why the owner's manual for your car specifies a torque value for the wheel bolts, usually 60 to 100 foot-pounds for a passenger car. Too little, the wheel can work loose, which is catastrophic. Too much, you can stretch the bolt past its yield point, weakening it, or warp the brake disc with uneven clamping. Failure goes both ways. In critical structures, aircraft engines, pressure vessels, bridges, engineers do not rely on torque alone. They use more precise methods. Ultrasonic bolt length measurement, the turn of nut method, tension control bolts with a special tail that shears off at the target torque. A modern Boeing 787 is assembled from roughly 2.5 million fasteners. Each one is a torque problem during installation, a fatigue strength problem during service, a materials compatibility problem in design. Titanium bolts in carbon fiber panels, you have to think about galvanic corrosion, about the difference in thermal expansion, about hole quality, because composites can delaminate if you drill carelessly. Every hole is a stress concentrator in a structure that experiences bending, twisting, and pressurization loads millions of times over its service life. The engineers who designed those connections stand on a pyramid of knowledge stretching through the crash investigations of the de Havilland Comet airliners in the 1950s, through August Vohler's fatigue tests on railway axles in the 1850s, through Navier's beam formulas, through Euler's mathematics, and back to Archimedes, reasoning about levers on the shore of Syracuse. August Vohler, a German engineer working on the Prussian railways in the 1850s and 60s, made a discovery that changed engineering forever. He found that metal can fail at a load far below its static strength, if that load is repeated enough times. A railway axle that easily supports the weight of a carriage can snap after 1 million rotations, simply from repeated bending. This phenomenon is called metal fatigue, and before Vohler, nobody knew about it. Vohler ran thousands of experiments, loading metal samples cyclically, bending and straightening them again and again, millions of times. And he plotted curves, showing at what load level the material would survive an infinite number of cycles, and at what level it would fail after a certain number of repetitions. These curves, Vohler curves, are still used by engineers worldwide when designing anything that experiences repeated loading: bridges, airplanes, engines, wind turbines, oil platforms. A century after Vohler, his discovery received a tragic confirmation. In 1954, 2 de Havilland Comet airliners, the world's first jet-powered passenger planes, broke apart in mid-air over the Mediterranean. The investigation showed that the cause was fatigue cracks starting at the corners of rectangular windows. Each cycle of pressurization and depressurization in the cabin, with every climb and descent, created microscopic stress at the window corners. After thousands of flights, tiny cracks grew to critical size, and the fuselage tore open. After the Comet disasters, the entire aviation industry overhauled its design approach. Windows became round or oval, no sharp corners to concentrate stress. Mandatory inspection programs for fatigue cracks were introduced. The design philosophy changed. It was now assumed that cracks would form, and the structure had to be designed so that a crack could grow without causing catastrophic failure, until it was found during a routine inspection. This approach is called damage tolerance, and it underpins the safety of every airplane you have ever flown on. That is the very pyramid of knowledge we are talking about. Vaughn discovered the phenomenon. The comet revealed its lethal consequences. The aviation industry created standards and procedures to prevent it from happening again. Each layer is a response to the previous one. Each lesson, paid for with someone's life, becomes a rule that saves lives in the future. And this brings us back to Petroski and his idea of applied anxiety. An engineer must worry. Worry is not a weakness, it is a professional tool. An engineer who does not worry is dangerous, because he has stopped asking himself the question, what if I am wrong? A good engineer asks that question constantly and designs the structure so that the answer is never fatal. The Tay Bridge in Scotland collapsed in 1879 during a storm. A train with 70 passengers fell into the river. The investigation showed that the designer, Thomas Bouch, had underestimated the wind loading and used defective cast iron components. The quality of the casting was poor, with voids and cavities in the metal weakening it. And quality control was inadequate. Nobody checked every component. After the Tay Bridge disaster, new standards for wind loading and material quality control were introduced. Those standards protect us to this day. And a direct line can be drawn from the Boston molasses disaster to the engineering stamp that appears on every construction drawing today. That stamp means a licensed engineer has reviewed this design and assumed personal legal responsibility for its safety. It exists because in 1919, a tank built by a company treasurer with no engineering education burst open and flooded a residential neighborhood with 12,000 tons of molasses, killing 21 people. The knowledge was available. The formulas existed. The principles were understood. But they did not reach the person making the decision. And after that, after every such case, society erected one more barrier between ignorance and catastrophe. The Boston molasses disaster, the Tay Bridge, the Comet airliners. Each of these tragedies is a link in a chain leading to the world we live in today. A world where buildings stand, bridges do not fall, planes fly, and we do not even think about it. We do not think about it because generations of engineers learned from other people's mistakes and built better, more reliably, more safely. And here, perhaps, is the most important thing to say about engineering after everything we have seen today. Engineering is not a science of calculations, and not an art of beautiful structures. Engineering is a tradition of passing knowledge from master to apprentice, from one generation to the next, from one disaster to the next safety standard. This tradition stretches in an unbroken thread from the Roman mason, who knew that archstones should be 1/20th of the span, to the engineer calculating the fatigue life of a Boeing 787 wing. Formulas have changed, materials have changed, scale has changed, from a 20-foot span to a 200-mile subsea pipeline. But the method, making decisions under uncertainty based on the best available knowledge, has stayed the same. We have come a long way, from the stone arch of a Roman aqueduct to a concrete cylinder on the floor of the North Sea. From semicircular stones laid on wooden centering in the 1st century AD to fabric a fraction of an inch thick, suspended on steel cables in the 21st. From a mason who built by rules he could not explain to an engineer modeling how a structure behaves under 5 million waves a year. Every structure we have seen solves one task. Take a force, gravity, wind, water pressure, the weight of a train, the impact of a wave, and guide it along the path of least resistance to the ground, to rock, to the seabed. Every stone in an arch, every flying buttress of a cathedral, every rivet in the Eiffel Tower, every concrete leg of the Troll platform is one link in that chain. If every link holds, the structure stands. Quietly, invisibly, unnoticed. Year after year, decade after decade, sometimes century after century. And every one of those links is someone's decision. Someone chose that wall thickness. Someone calculated that torque setting. Someone determined that the wall should slope 1:5. Someone decided that the archstones should be 1/20th of the span. Someone thought to put steel bars inside concrete. Someone worked out how to lock lighthouse stones into a puzzle so that no wave could pull one free. Someone designed a ball joint 33 feet across and weighing 680 tons. The single point through which 35,000 tons of storm loading pass into the foundation. All of these people, from the unnamed Roman builder on the site of the Pont du Gard to Master Gerhardt laying out the plan of Cologne Cathedral, from Brunelleschi convincing the Florentine commissioners that the dome would stand, to Freycinet raising a concrete arch with jacks over a river, from Smeaton locking the stones of his lighthouse into a puzzle in the middle of a raging sea, to Peter Rice hanging a glass wall on joints the size of a human hip, from Vaughn standardizing fortresses across France, to the engineers of Troll A pressing 19 concrete cups into the seabed at a depth of 1,000 feet. All of them were doing the same thing. They imagined the forces that would act on their structure. They imagined everything that could go wrong, and they found the shape, the material, and the connection that would hold. Not the perfect solution, the best available one. Not an absolute guarantee, a reasonable confidence. With each generation, that confidence grew. New materials, new methods of calculation, new lessons drawn from other people's mistakes. But uncertainty never fully disappeared. The soil under the foundation remains unpredictable. The wind remains unpredictable. Time remains merciless. And the engineer continues to do what all his predecessors did: make a decision under incomplete knowledge, leaning on experience, calculation, and professional intuition sharpened by generations. Right now, as you lie here listening to this, forces are traveling through the building you are in. The weight of the roof presses on the rafters. The rafters pass the load to the walls. The walls carry it down to the foundation. The foundation spreads it across the soil. The soil accepts and holds. Every brick, every beam, every bolt. One link in that chain. You cannot see those forces. You cannot hear them. But they are working. right now, this very second. And they will work all night while you sleep. Someone once calculated that beam. Someone chose the thickness of that wall. Someone tightened that bolt to the right torque. Someone checked the bearing capacity of that soil. You do not know those people. You will never learn their names. But their work, quiet, invisible, precise work, is holding you right now. As it held you yesterday, as it will hold you tomorrow. Somewhere right now, in the North Sea, a wave is crashing into a concrete leg of the Troll platform. The leg holds. It was designed for 5 million waves a year. Someone calculated that number. Somewhere in the Netherlands, a rubber gasket on the bottom of the Rotterdam floodgates is waiting for the next storm. It will compress under the weight of the steel wall, and it will create a seal that separates a country from the sea. Someone designed that gasket. Somewhere in Florence, Brunelleschi's stone chains are still pulling the dome together, preventing it from spreading, as they have been doing for 500 years. Somewhere in Cologne, a mason is replacing a weathered block on a cathedral that has been under construction for 800 years. Somewhere in the south of France, water could still flow through the channel of the Pont du Gard if someone opened the valve. The arches are ready. They are waiting. And here, in this room, beams carry your roof. Walls carry the beams. The foundation carries the walls. The earth carries the foundation. The chain is unbroken. It is working. Quietly, reliably, invisibly. Engineering is a quiet art. It works best when no one notices it. When you walk into a building and do not think about whether it will stand. When you cross a bridge and do not think about whether it will hold. When you fall asleep under a roof and know without a single conscious thought that it will still be there in the morning. Let that thought stay with you. For thousands of years, people have been learning to build, failing, destroying, rebuilding, and learning again. Every standing bridge is a monument to a bridge that once fell. Every surviving lighthouse is an answer to a lighthouse that the sea swallowed. Every safe building is the result of centuries of accumulated knowledge, compressed into a handful of rules, calculations, and intuitions. And all of it is working right now, quietly, reliably, invisibly. You do not need to think about it. You do not need to remember anything. The structure is doing its job. The bolts are tightened. The calculations are checked. The ground holds. Just breathe and rest. The engineers have done their work.